Did the farmer perform tillage in this field? That's the question that me and my co-authors are trying to answer. Oops. Okay, so what is tillage, right? So it's basically when you revolve the soil and then you expose the soil and put up the crop or whatever is on top of it, you bury it, and that material is going to get decomposed, right? A no-till practice is when you don't do this type of practice, you don't revolve the soil, and you plant on top of the residue. So the residue is going to cover the soil, and that's going to be a barrier for erosion. It's going to help your soil health as a whole. It's just a good practice for thinking about long term. This is how the crop residue looks like when you take a picture of the soil. So in the first image you can see the soil is completely exposed. So in that picture you can see that there was plow applied to that soil, and the crop residue there is, you consider a plow tillage when you have from 0 to 30% crop residue cover, right? And the last one we can see, that's supposed to be 60 to 100%, I'm sorry. But no-till practice, right? When you have a completely covered, or partially from 60% to 100, covered with any type of residue. It could be corn stalks, it could be soybean stalks, it could be cover crops, right? But in this case, so it's not that we're trying to see which type of cover crop we're talking about. It doesn't matter. It doesn't actually matter, right? And the principal thing about no tillage is because it promotes higher soil organic carbon, increasing infiltration, improving soil health. It helps with the climate challenges that we're having right now, and particularly NASA is interested in this result because they're trying to calculate the carbon sequestration pool that agronomic fields have, right? So those inputs, those maps, that tells you how much percentage the soil is covered, it's going to be input for a SWOT model that NASA is doing, right? This work is actually upscaling the work done by LAMP in 2025 to Landsat and Sentinel, which is an open source satellite imagery, right? So he used WorldView 3 images, which is a very particular type of satellite imagery that has a higher spatial resolution. What that means, the pixel size is more, it's different, right? So this is a Landsat and Sentinel. We use HLS, which means that is harmonized, so that the pixels are aligned with each other from Landsat and Sentinel. And this is a WorldView 3 image, so it's more detailed. You can see better, right? So his predictions were my ground truth. So whatever he predicted, right, using multilinear regression and a particular vegetation index that could see what is the crop residue, he reached R-squared of 98% using that type of imagery, right? And now we want to upscale that for free satellite imagery HLS. I'm going to refer to Sentinel and Landsat as HLS. WorldView 3, I mean, the second reason why the work he did was so particularly good, it was because the higher spectral resolution in the narrow bands, and Landsat and Sentinel doesn't have that, right? So if you see in this part of the spectrum particularly, which we call SWIR bands, the short wavelength infrared, we can see there is a jump between S2 and S3. So the light gray is from WorldView 3, and you can see particularly this jump in the SWIR wavelength. So this is where we can actually differentiate what is soil and what is cover crop. The third reason why we wanted to upscale this work is because of the size of the image. You can see the blue one here is the WorldView 3, and the Landsat is the the yellow one, so it's much bigger, right? That means that we can use less satellite image. You know, WorldView 3 is a purchase product, so we have to purchase a lot of image to do the whole Delmarva Peninsula. This is the area of Delaware. This is the Delmarva Peninsula. Delaware, Washington, Virginia, a little bit of Virginia, that's true, but unfortunately we're not using Virginia because there's not many croplands there, so we decided not to use. And Delaware, Virginia, and Maryland. All right, so going through to materials and methods, right? This is just a nutshell. We chose the years of 2017 and 2022. I'm gonna say this, it's because of the wetness in the images that we could introduce, and I'm gonna explain that further, but just understand that 2017, 2022 had a difference in wetness. We're using bands and vegetation indexes. We do a lot of pre-processing on those images. So we only have farmlands, whatever is a building, you know, a forest, whatever it is, we took out of that analysis. We also took pixels that has any DVI higher than 0.4. Why? Because those have a high biomass, a green biomass going on. So we don't want that in our analysis. Transform that to a tabular data. There are estimations using machine learning algorithms. I'm going to present here the results for random forest and XGBoost. The next one's going to be neural networks. I did have some pre-results with neural networks, but I'm using TensorFlow, and it's not being a good deal right now, so I'm going to try to do in PyTorch to see if I get better results. And then the farmland maps, right? So what do I mean by wetness in the image? So let's say this is the WorldView 3D acquisition, right? So when I get the HLS image on the same day, the difference in dates are 0, it means that the wetness in the images is gonna be the same. But if I get before, right, different in days after or before, right, I'm gonna have a difference in days, and that's gonna introduce some differences in wetness. So I built up an analysis to try to understand the difference between in wetness in the images, calculating the last 7 days, the cumulative precipitation in the last 7 days, and the difference between the days of acquisition, right? So this is just like a sketch to, you know, try to explain what was going on. But okay, let's see the difference in wetness, right? So we can see that 2017, 2022. In 2017, right, I have a cumulative precipitation between WorldView 3 and HLS of 42.7, and the difference in days was 18 days, in absolute days, right? So the date of acquisition of HLS and WorldView 3 were different, and that introduced wetness and other types of management systems in the farm. So that's going to change the landscape, and when my landscape is not the same, that introduced error to my model. And in 2022, I have no difference in days and no difference in precipitation cumulative, right? So the wetness in the image is the same. And I mean, there is no farm procedure that was done in those lands, so there's no landscape changes. This is the result for random forest in 2017, right? So I got an R-squared in random forest of 0.57 and 0.59 when XGBoost was performed. So we can see like XGBoost is performing a little bit better. Same happened with in 2022, but when you don't have the wetness in the image, the R-squared gets better by 10%. So this is 0.65 and 0.62 for XGBoost. When we, and that's for Sentinel data, right? And now for Landsat imagery, right? We get, the same type of accuracy, 57, 59, and Landsat, so Landsat In 2022, no wetness in the image, we got 88 and 88%. So much better predictions, much better accuracy. So high surface moisture levels introduce interference, as we can see in the year of 2017, right? And our models demonstrated comparable performance in 2022 when no surface moisture interference was observed. This is an analysis that is called SHAP values. I know that usually people tend to present mean decrease accuracy, but because I'm working also with neural networks, I want to be consistent throughout my analysis, and that's going to be my next analysis. And so I decided to use SHAP values. We can see that MCRC, which is a vegetation index, is that it's an indication of crop residue cover. It's a modified index for crop residue cover. Was the most important, regardless of the year, right? So in Sentinel, MCRC was the first most important variable for any condition. And then we have SWIR-A for 2017 when we have moisture. So SWIR-A is a SWIR wavelength infrared angle index that is particularly looking at that part of the spectrum where we have the difference, the jump, right? It's not very clear in Landsat and Sentinel, but still, MCRC and SWIR-A are indexes that use the SWIR infrared in their calculations, right? So we see the important, and they're not as important. So that's SWIR-1, that's SWIR-2, and the indices were more important, right? So we can see that indices are doing a better job. So vegetation indexes were essential for the models, especially with the Sentinel data. Now we're gonna talk about the Landsat, and just to explain a little bit of the difference between Sentinel and Landsat is because of the thermal bands. So thermal bands, it's particularly interesting because they can tell you how, the temperature of that, that image, right? So the soil or residue. And we can see that the thermal bands were particularly more important when the soil was wet. So when we have surface wetness, the thermal bands were very important. Vegetation indexes and thermal bands were essential for the models with Landsat data, especially under high surface moisture conditions. As a conclusion, all the models were able to do the prediction. XGBoost, particularly XGBoost, had a slightly better results even when the data set has surface moisture interference, and the temporal gaps between HLS and WorldView 3 acquisitions may introduce variability in surface conditions, right? Such as increased soil moisture or field operations. So I'm talking here about moisture conditions, but that also goes for any type of field operations, which can negatively impact the model performance due to discrepancies in input, reflectance data, and vegetation indexes. This work is going to be published in the Science of Remote Sensing. These are those models that I built was for each year, right? But the idea, the major idea is that we can combine all the data sets so the model can learn any condition and see if it can generalize well. So, if you need, a map for tillage intensity, it's going to be public available, and as well as the code. Thank you. Any questions?
1 minute. One quick question.
Yes, thank you for your presentation. Can you estimate the amount of crop residue cover at the time of planting?
Yeah, so that's the idea, because the timing of the data acquisition, the satellite acquisition, was between May and June. So we believe that's when farmers are starting to prepare for for planting, right? And particularly, that's the reason why field operations can happen between when you have the gap and the data acquisition. So yes, it's on planting day.
Thank you. Our next speaker is Abhilash, and he will be talking about advancing non-invasive peanut maturity prediction using aerial multispectral imagery and weather data.
Thank you. Good morning, everyone. I hope you're having fun with this last day of the conference. So thank you very much. I'm going to present on behalf of my student, Satish Raymond, who is working as a PhD student on this topic. We are trying to predict maturity of peanuts, a crop that grows below ground, and using aerial imagery and machine learning algorithms. So yeah, just brief contents about it. We'll talk about the problem background, what were the goals and objectives, the methods adopted, the results, and finally the conclusions of the study. So peanuts, they have a distinct behavior of being indeterminate, meaning these can continue to keep growing, keep producing flowers, keep producing peanut pods till the climate conditions are favorable. Now that becomes challenging for growers to determine when is the actual time they should terminate the crop growth and should harvest the crop. Now, for example, sometimes most of the peanuts, they can vary in terms of their spatial variations in the field due to microclimate conditions, due to soil conditions. So it might happen that part of your field is under-matured or part of your field could be over-matured. Now that becomes a big problem when farmers need to plan their resources better for precision harvest, and that's where we come in. So, conventionally, the peanut maturity is determined when by growers walking down the field of a 500-acre farm or a 100-acre farm, and they pick 3-4 samples from the middle of the field. They dig those out, they remove the peanut pods out of it, and then they use a pressure washer liquid like water, water at high pressure using turbo nozzles to kind of remove the outer layer of the peanut. So it has exocarp, the outer level, mesocarp, the middle layer, and the endocarp, the inner layer. So they want to remove the exocarp using that pressure water, and that exposes the color of the peanut pod, the actual color of peanut pod, which ranges from white, yellow, orange, brown, black, and that tells the maturity status. Now this entire process takes about 25 to 30 minutes per sample. Now imagine growers just take their decisions based on only one sample for the field, that could be 100 acre or 200 acre. Does that remain representative? Not really. How do we account for spatial variability? Now if growers want to be very much precise with that approach, they'll have to collect too many samples, and meaning too much of labor, too much of time. And that's where we are trying to kind of help with using aerial imagery and machine learning to get this problem solved. So yes, advantages of aerial imagery, it can give us large amount of data in less amount of time, of course in different spectral bands. And so goals for our study was developing high throughput precision maturity mapping techniques using aerial spectral imagery and machine learning. Specific objectives were about evaluating multi-view machine learning models. And then secondly, we wanted to also generate prescription maps using those ML approaches and then validate those as well. So these are kind of maps that can be used by growers directly to plan their operations. So we are trying to have an end-to-end approach, not just limited to research, but actually translating it to the end users or growers. So we totally had 7 different trials across 2 states, Virginia and North Carolina. We evaluated a cultivar called Bailey 2, which is a very important peanut cultivar grown in the Virginia Carolina region. It has a higher crop value because of its size and the crunchiness, so it's very highly rated crop. And then we captured images at about 1 centimeter per pixel of resolution multiple times in the growing season. And every time we kind of sampled peanuts from those grounds. So the number of samples that we captured for only one cultivar was around 300 samples. We have been conducting this study for past 3 years. Till now we have accumulated over 2,700 samples. Now remember that number that I told, it takes 25 to 30 minutes to just get ground truth data for one sample. We did that for 2,700 samples. So 2,700 times 25 if you are an expert. So that was the amount and the effort that was spent. Now this shows the transition of maturity based on color. White, yellow, orange, brown, black. Black is like terminate the crop growth. You need to harvest right now. If the crops are harvested at under matured stage, there could be a lot of moisture in it, so there could be added fungal infection problems. And also growers would have to spend extra resources for artificial drying, like using propane gases and burning things around. If it is over matured, then these pegs or these pods will become loosened, so while harvesting they can remain under the ground and it may never be harvestable. So that's again, that's why it is very important to find out optimum interval of harvest period. So yes, in terms of aerial imagery, we got all these indices computed: NDVI, soil adjusted vegetation index, normalized difference, Reged index, and many others. And then we also acquired weather data, which is very important. Earlier, in the year one, we just evaluated spectral imagery, but then we also incorporated the weather data because that's a big factor driving the crop growth. So we computed growing degree days. That is an accumulated indicator of the heat units within the crop. And this was a modified index value where soil temperature, relative humidity, and air temperature were used together. So we had more comprehensive effect of the weather to the crop. And then we calculated an index for maturity called peanut maturity index, which is the average of orange, brown, black, sum of these three, and divided by total number of pods. So for every peanut pod, we just term those as pods. So, and generally, when the maturity reaches like 65 to 70%, that's when growers decide that let's go and harvest. But that's based on only one side. So, and this is the architecture of multi-view stacked ensemble learning. Now, we grouped all of our variables. So let me just mention about the variables. Our first variable category was raw reflectance bands coming from drone imagery: blue, green, red, red-edge, near infrared. The second category was vegetation indices, NDVI, SAVI, NDRE, and other indices. And third group of variable was accumulated growing degree days. Now, that's where the multi-view part comes. We categorized, or we grouped all variables into three groups: reflectance, vegetation indices, and growing degree days. And on every variable, we ran independent machine learning algorithms, 5 machine learning algorithms: K nearest neighbor, random forest, support vector machine, XGBoost, and neural network, individually on every category, to predict peanut maturity at their individual capacity. Once they did that, we combined the predictions from all these three categories, again using machine learning. Now that's called meta learner. Initial stage is called base learner. And that's how we kind of moved into multi-view stacked machine learning approach. And then eventually, we kind of converted these into precision maps and also evaluated what was the accuracy of those maps. So this is a performance of top 5 base learners. Base learners meaning machine learning or individual variable categories. These are the combinations. So as we see, support vector machine, neural network, and random forest. This combination performed the best, giving us R-square value of 0.72. And we believe that this is a very good accuracy for a crop that grows below ground. So, this says that the SVM is about the reflectance values as inputs. Neural network is for the vegetation indices as input, and random forest is the best performing base learner model for growing degree days as the input. And it's also listed here: SVM for reflectance, neural network for VIs, and random forest for growing degree days. Now this image shows the feature importance for different base learners. Now this is for the reflectance, and it shows that green band had almost like 45% of importance in that entire individual base learner model, followed by red edge, then red, and then blue. Blue and near infrared. So that's what the combination of importance was. Looking at the neural network where vegetation indices were the inputs, green, red vegetation index was the best, or not the best, but most accounting for variability. That was the best performing variable. And the amount of importance was about 28%, followed by a mean simple ratio around 11%, and then so on. So yes, we also performed dimensionality reduction because we wanted to remove variables that were co-founding each other again and again. And then this is the performance of meta-learner. Meta-learner where all the outputs were combined from 3 independent base learners. And this is the average under each model. So meaning, under every model there were 125 models of base learners. And this is the average of 125 models. So it means that there could be a very highest performing model plus a lowest performing model. And the average was the best for support vector machine, where this is the average, or this represents total amount of like 625 models. So that was the amount of models that we trained for only one cultivar. And that was the mean roots mean square error. So this is the top 5 performing models: base learners and then the meta learners. So model number 1, model number 2, 3, 4, 5. So this is like view 1, where reflectance, the R square value in RMSE, just using reflectance as inputs. This is just using vegetation indices as input. This is using the weather data as input, and this is the combination of it. And we also see from this that the weather data was the biggest influencer in terms of maturity estimation. And this is like the final best performing model with base learners and meta learners. Base learners were SVM for reflectance, neural network for vegetation index as inputs, random forest for growing degree days. And then the meta learner was KNN, the best performing, that combined all the outputs. And we saw like view 3 is actually the growing degree days, the weather data, that accounted for almost like 82% of importance. And that's the biggest influencer, followed by the view 1, that is reflectance, around 13%. And then view 3 was the vegetation index, around 5% of importance. And this is the evaluation over test data set of the best performing model, where we received R square of 0.75 and RMSE of 21% around, which is very well acceptable by the growers. So growers really are looking forward to this information in implementing, because it saves them huge amount of time in their life. So after we kind of delved into predicting just using regression, we kind of converted those meta-learner, base learner combination, we deployed them to get into the maps. So this is the maturity status at 118 days after plantation. Maturity is somewhere around 30%, I would say. And this is after 133, where maturity reaches 0.5. And then this is at 146, where maturity reaches around 0.75 to 0.8. And that tells that what is the appropriate time for a grower to go to the field and start harvesting. And this is the mapping accuracy, where we saw an R square value of 0.89 and root mean square error of 18%. So we were pretty pleased with that. Now we are also repeating this for other cultivars. So total we evaluated 9 cultivars. This was only the result for one cultivar. So we are going to do this for 9 different cultivars. 5 are new breeding lines and 5 are the commercial cultivars that are grown in Virginia, Carolina region. Of course, we also want to have this approach very much translatable to other cultivars and in fact globally peanut growing regions. So in terms of conclusion, we had very robust model performance with highest R square value of 0.75 and error around 21%. Grower benefits, of course, this helps in identifying what will be the appropriate time for them to go for harvest. So we're also working for forecasting peanut maturity, because weather is a big factor, so we can forecast now. Future scope, we are also developing a tool, a web tool, where growers can actually just draw boundaries around their field that uses satellite data. So we are going to translate these drone-based models into satellite-based models, and growers simply draw the boundaries and they get to know what is the maturity stage so they can plan ahead, and that will be free of cost to them. And of course, we are still continuing our multi-state trials in three states in multiple locations in Virginia, North Carolina, and South Carolina. So we look very much forward to that. Of course, other cultivars, other participants are also, if they are interested, we can contribute, we can collaborate and take this move forward. So thank you very much, all these supporters of the program, USDA for funding, Virginia Peanut Growers Association for partial funding of this project, Peanut Variety Quality Evaluation Program. There's a designated program for this in Virginia and North Carolina and South Carolina. For more information, please feel free to write me an email and I'll be happy to answer any questions. Thank you.
We will hold on questions. Okay. Our next speaker is Anayat.
I'll be talking on behalf of Anayat.
Oh, no problem. Our next speaker is Pappu Yadav, and he'll be talking about early nitrogen detection in corn.
Yeah. Hello everyone. I'll be talking on behalf of Vinayak Rasool, is my graduate student. Integrating hyperspectral imaging and genetic algorithm for early estimation or detection of nitrogen deficiency in corn plants. So when we look at the map in the United States, these are the corn belt regions. You can clearly see the bushels per acre of corn has been pretty unstable, not very stable. Of course, many factors are there. Anything related to weather-related issues, disease-related issues, pest-related issues, even weed-related issues. So bushels per acre, when we basically see close to 150, 160 on an average bushels per acre. That's what we have been seeing. But that's not enough. When we also see in the state of South Dakota, soybean corn production hasn't, like in terms of bushels per acre, hasn't really been stable or hasn't really gone higher. It's even though corn and soybeans are rotated and they are major crops even in the state of South Dakota. So what could be the possible reason that we can actually try to manage this, and can we increase the increasing demand with growing population? So we have to take care of the yield. We have to find a solution to improving the yield. So when you look at the corn production, primarily three major fertilizers play a very crucial role in the growing phase of the corn plants, and they basically are potassium, nitrogen, and phosphorus, NPK fertilizers, out of which nitrogen plays a very crucial role in the growth of the corn plants as well as in the growth of their kernels and hence the yield. So when we look at these corn plants, when they get stressed, they basically, when they are nitrogen stressed, they show some kind of symptoms and they eventually lead to deficiency in the yield. So, but there are corn plants, when you see, they grow over different growing stages, from the vegetation stage to the reproductive stage, and from V3 to V6 is when the growers or farmers, they can take steps to add the deficient nitrogen. That's what normal the growers' practices are. And usually the normals, they before growing any kind of plants, they already apply their fertilizer before actually plantation. But there can also be taken steps when the crops are actually growing for in-season nitrogen management. So what can we do for that? How do we actually detect those early deficiency of nitrogen in the corn plants? We can use some techniques called hyperspectral reflectance imaging. And you can see on your top left, bottom left, there is a spectral reflectance that can capture primarily the chlorophyll. They reflect around before the 750 nanometer range. When we go in the NIR range, they start reflecting more, and hence those are the regions, or even some subtle minute reflectance beyond that region can be captured using hyperspectral system beyond our visual observation, and hence we can capture those minute deficiency, which can be ultimately used for management practices. So let's see how corn plants, like they look like, or what happens when they are nitrogen deficient. So first of all, they also show some visual symptoms on their foliar surfaces, like the leaf surfaces. They start yellowing, their kernels are reduces, and their overall biomass of the volume also gets reduced, and that ultimately results in the deficiency of the yield, right? The deficiency of corn yield. So on the top left, you see overall nitrogen cycle. Due to time constraint, I won't go in much detail, but what I can focus you, if you look the graph over on your bottom, on the right side, on the bottom left, just by applying nitrogen at different growth stages will not result into higher yield. That's what that particular study says. So how much nitrogen needs to be applied at what growth stage that can enhance your yield is very critical. Just because they are nitrogen thirsty, you can't just feed them nitrogen and expect a higher yield. So two important things from this study, what can be seen that what is the growth stage that you need to target and at what rate you need to target. These are the two critical factors that will play in enhancing or boosting a corn yield. So you can also do nitrogen side dressing. People, growers and farmers, they follow. That's like done during the growing phase, and they can use some boom-based applications, and using those kind of techniques, they can do some side dressing of nitrogen. So what are we proposing through this study is that, of course, this study we have done in the field scale as well as greenhouse, but this particular study is focused on the greenhouse trials. We actually did some treatment of corn plants with 3 different nitrogen rates. 0N is the control, and 50 N pounds per acre, and 100 N pounds per acre. And we had like 3 replicates of that, and we cut those leaf samples, we scanned through our hyperspectral systems, and we developed our AI algorithm to capture those subtle differences in the nitrogen through the foliar surfaces. So overall goal was to develop a system that can actually tell us nitrogen deficient corn plants at as early growth stage as possible, primarily targeted between V3 and V6 growth stage. So the specific objective for this particular presentation is going to be to develop a very novel image processing pipeline using hyperspectral imaging system and the CNN, AI-driven CNN, so that we can actually show the differences between nitrogen deficient corn plants. There is a sub-objective tied to this particular specific objective, which is, can we also discriminate the 5 very important spectral bands that can help us discriminate these nitrogen deficient corn leaves. So this is the workflow pipeline. As you can clearly see, 0N, 50N and 100N treatments that we did in the potted corn plants. Then our graduate student, they basically just cut some of those leaf samples, and they cut into a very squared shape, and they placed in the hyperportable hyperspectral imaging system developed by USDA, Beltsville, Maryland. And we are working also with University of Florida on this project. So the image that you see over there, then we brought those samples and we scanned them, and the red one that you see, that's the hypercube across 348 bands that we developed. But out of this, we found that from our previous study, published study, some of the earlier bands, first 6 bands and the last 8 bands, they had some issues. So we tried to get rid of those bands, and then we used genetic algorithm to select the most important bands. Now, whoever saw my last presentation yesterday, we used a different approach to select the bands, which was PCA. But in this particular approach, we use genetic algorithms. Genetic algorithm is nothing but a search algorithm. It basically just tries to find out of those 348 combination of bands, which are the best combination of bands. And then we try to use custom CNN to capture some spatial features. And then we train 10 different machine learning classifiers, and these are traditional machine learning classifiers. And we did the classification of 0N, 50N, and 100N nitrogen corn leaves. This is how the system looks like. It's a 395 to 1005 nanometer based system. And then we have a head wall based hyperspectral system. Actually, this system can do both hyperspectral reflectance as well as fluorescence, but we just focus on the hyperspectral reflectance aspect. The video that you are seeing is actually on a citrus leaf samples, because they are of course not corn samples, but this is just from the video that we did another study on a citrus in Florida. So let's little bit quickly walk through what exactly genetic algorithm does. For this, we actually use DEEP, which is a distributed evolutionary algorithm in Python. It's a package that you can implement to implement your genetic algorithm search method. And we use the 2 key, these are the key operators that we use. So again, these are the functions within that package. CX2 point for crossover mutation, uniform mutation selection, we use this particular uniform int as a factor within the function, and tournament is like for selection criteria. So what is the difference between the PCA method that I presented yesterday and this genetic algorithm is that is a linear transformation without understanding if it results a best classification or not. Whereas in genetic algorithm, it actually does classification with all the combination of those 5 bands, and then it chooses the best one. So that's the advantage of this. And these are the different, again, 10 different classifiers. As you can see how they seem, and basically what you are seeing over there, those green and the blue slices, they are the classifiers. So they are the hyperplane of the classifiers. So they basically separate the two different features. So we are only representing with two different band features, you can imagine, and then there is a classifier. That is how these all 10 different classifiers they work. Same thing goes for these other remaining 4 classifiers, and the way they were evaluated, the performance was based on precision recall F1 score and overall accuracy. So as you can see over here, we are also showing an example of random forest classifier. When we do some scatter plot of 2 different feature vectors, then you can see how they change with 5-fold cross validation. Because on top of that, we also did 5-fold cross validation accuracy. So with genetic algorithm, on top of that, when we trained the machine learning classifiers, we went through 5-fold cross validation. And we selected 5 bands. So as you can see, at V3 growth stages, those are the 5 bands we selected, which are lambda represented by lambda 1 to lambda 5. At V4, again, another 5 bands. So they were not exactly the same. So there was some minute differences in the selected wavelengths. So what do we see when we see at the V3 growth stage? As you can clearly see, these are the results that we got from different classifiers. We're using the all these precision recall and overall accuracy. Similarly, we also did some average mean squared error on the bottom left. You can clearly see most of the classifiers that resulted in almost perfect classification accuracy. Similarly, only the QDA and some other classifier, which is the non-linear SVM or the RBF SVM, resulted in slightly lower accuracy, and then MSE was slightly higher for the QDA and the RBF SVM. So overall, it was slightly consistent, except the fact that the overall accuracy, when we compared here, you can clearly see that at lower V3 or V4 stages, we got slightly better result compared to the V6. So we see a slight decreasing trend as we went to the increasing growing phase. So what is our findings? We were able to develop the pipeline that can actually integrate genetic algorithm, hyperspectral imaging, as well as AI to actually discriminate the 3 different on nitrogen treatment of the leaf samples. We were able to find that at V3 stage, we almost achieved perfect classification accuracy with almost all of the classifiers except for QDA and the other one. Whereas the model performance slightly decreased as we went through V4 and V6 stage. So random forest and the RBF SPM, they were the top performer for if you do the overall classification accuracy. So what is going to, how the future work might look like? So this platform that you see over here, that might actually, in the Omega platform, we have developed for precision spray application. Unless some growers want to, of course, it's not a very commonly practiced liquid nitrogen application, only granular nitrogen application is done. But we can just modify this, we can use the 5 bands that we selected, and we can replace our RGB camera right now with those multispectral filter based camera, and then we can implement this for real-time application. Would like to acknowledge all the collaborators on this and South Dakota Nutrient Research and Education Council, including the NIFA and the UFIFS. Thank you, and I'll be happy to take questions.
We have time for a couple of questions.
Yes, Hussein.
Thank you, Papa. Actually, the question that I have, maybe there will be a couple of questions, but I'm trying to understand here. You are trying to find nitrogen deficiency in whole plants. So the quick question is that when that happens first, close to the ground or upper leaves?
Yeah, basically the nitrogen deficiency normally when the growers they implement in the soil, right?
Okay.
When they prepare.
So it should be.
So it starts and foliar symptoms starts appearing little later. So as before, normally growers they scout the field and they see some visual symptoms.
Sure, visual.
Yes. But what we are trying to achieve here is, can we find before the visual symptoms appear?
Ultimately, are you going to fly UAVs on top of the field?
Can be done, implemented. This has the potential for both applications, but currently our focus is on the ground-based.
Because if you want to fly a UAV on top of it, you will see the upper leaves, not the bottom leaves.
Right.
On the other side, if you want to detect it with UGVs, UGVs are slow and then probably it will take some time to drive it through the field and measure how much the grow spacing is. So just some challenges are over there. If we can implement this technology, that would be great, but some challenges in terms of speed and how, if you want to speed it up, you will not see that very realistic. If you want to go with UGV, you have to slow it down.
Right.
So there's a
Yeah, there's a
problem there.
trade-off with that thing. Yeah, I know.
absolutely.
To make it scalable is always
Yeah.
something like, challenge. Yeah. I totally agree with that. Yeah.
Appreciate it.
Sorry to interrupt. Do we have the next speaker from University of Florida? Steven Yu? Okay, so I think the next speaker is missing, so we can continue with the questions. I actually have a question online for you.
Okay.
Does anyone have questions for Dr. Yadav? And there is a question for you as well.
Happy to.
So, let me read it out loud so that they
Yeah, sure.
So, the question for Dr. Yadav is, does the GA take care of the spectral bands that have the best response? I think PCA would pick the bands with most information, but not necessarily pick the most responsive band. How does GA perform compared with PCA for that purpose?
Yeah, that's excellent question, and actually it's again part of the study. We would like to have a comparative result. So for the yesterday's project that we saw was for completely different project, but for this particular project, we are going to do a comparative analysis on that. Theoretically speaking, PCA is a linear transformation. So what it basically means that if I have one variable increasing, the other variables would linearly increase. So what it means in this context is that the spectral reflectance that we get for a 0N cone versus the spectral reflectance for a 50N cone versus the spectral reflectance for 800N cone, they should actually linearly increase or linearly decrease. But does that necessarily happen? We don't know that yet. That's the reason why genetic algorithm is, at least theoretically, we assume that it should perform better, because what it does, it actually does classification with the random combination of bands, and then it picks up based on the classification result rather than just based on the transformation result. So theoretically, what our assumption is, GA should perform better rather compared to PCA, at least in this case. But if they are linearly increasing, if we happen to see a linear response in the reflectance, then probably PCA might work better. So that's part of the research. We don't know the answer yet. Yeah.
Any more questions? I have a quick question. So, what about which leaf was selected for the
Yeah.
imagery?
Yeah, that's a great question. So we always selected a third leaf from the bottom.
Any specific reason?
No, randomly picked, yes.
Because of the dilution that happened with nitrogen, that can
Yeah.
be a
Yes.
very, very good thing.
That's right. So to not make any result biased, we actually did some random sampling, yes, on the which direction of the leaf to pick from. Yeah.
One more question. Thank you.
All right, thank you.
Question for Dr. Chandra is, would you compensate the sun shade effects during the multi-view analysis? Oh, Chandel, sorry. My
No
bad.
problem. Well, we actually trying to kind of image near the solar moon where the shadow effects are minimal and the sun is directly over the crop. So that's our focus. That's our focus for now. But again, this is something that we can look into influence. But achieving like 0.75 of R square value with 3 of the primary factors, where weather is trying to indicate itself as the largest contributor to 80%, we feel that the influence of that particular sun angle would be lesser, but certainly we can evaluate. Any more questions? Yes, please.
You mentioned about microclimate.
Yes.
Could be a factor. Do you use multiple soil temperature probes in your studies?
So yes, that's a good question. The source of weather data. We have not used in-field soil sensors or in any kind of that. We have used remote sensing based data that is coming from NASA's SMAP that gives us soil moisture at root zone level, soil moisture at surface level. So we are taking the median of soil moisture in that 2 meters of depth, as one variable, and then the relative humidity, air temperature, that is already available at every site we are having our trials. So that's the source of data.
So the ground truth data resolution was 1 centimeter you mentioned?
Not the ground truth data, the aerial imagery
Yeah.
was 1 centimeters per pixel. And then, we kind of sampled the peanuts first, and then there was this kind of a void created on the canopy. So we flew before sampling and we flew after sampling. So we kind of marked that area where we picked the samples from.
How much was the area?
Well, it's not fixed. I mean, we were targeting at getting 3 to 4 plants every sample. So for example, our plot sizes were 3 feet, like around 6 rows in one treatment, and then around 50 feet long. And then we used to sample randomly from different locations. So
based on the the image, satellite imagery, and the resolution that you are saying that it was 1 centimeter, like comparing of these or correlation of with the ground measurement, there should be some correlation.
So there are 2 parts of this study actually. What we presented was based on aerial imagery coming from drones. So we had the control over it.
Which was how much like the area?
So you're talking about number of pixels kind of thing?
Yes.
So for one sample it would be say maybe 300 pixels at least.
Yes, because we would, as you are saying, that it was randomly on the ground.
Yeah.
But with the aerial imagery, with the rows you were taking, there would be different pixel size, different
Yes.
resolution.
Yes.
That how you made it like justified in your study that okay, this much resolution, this much pixel size, we get to the drone, and this much is on the ground we have.
So let me try to understand this first. So precisely if I have to normalize what amount of area we captured on ground was about 1 square feet, say. Okay. Now in 1 square feet, we had a pixel resolution of 1 square centimeters. Now 1 square feet is like 30 centimeters times 30 centimeters. That's 900 centimeters square. So we had at least 900 pixels on one area of samples that we collected. So we had enough of ground truth information to validate our findings. I hope that answers.
Yeah, thank you.
Any more questions, please?
We have time.
Yeah.
What is your KP to 20% normalized square translate into number of days prediction accuracy?
Okay, so this percentage that we showed here is the difference between the actual maturity and the predicted maturity. It's not between the number of days yet. We'll be going towards that. That's our next step. Like forecasting maturity, depending on in how many days the maturity will occur.
Do you have some sort of speculation at the moment?
Given we still expect the same number of error to be precise, because we have brought down this error right from 56% to 24% and now to 20%. This is the 4th year of study that we'll be repeating. So we are extensively behind. We are very much dedicated towards this. So we are expecting that it should be, like, say, at 1 to 2 days of an error is maximum is what we are expecting from forecasting. Yeah, and we believe that this kind of study, especially when crop grows below ground, how do we make an estimate just by remotely sensing it? That's the big part. And my students keep saying even 10 plus years of data is not sufficient, so we should keep doing this. I said you need to graduate first and then we'll take care of it. So, but yeah, I mean, this is something where we have literally gotten the feedback from growers and crop consultants that if this tool becomes real, that will be a big blessing for us. Precisely, if growers have to get very accurate estimates of peanut maturity over time and over space, they'll have to invest in total in Virginia $250 million every season. That's an impact of this study, where we'll make it for free, we just draw the boundaries around it, and they are very much happy with even 30% of accuracy, because they don't want to, kind of just keep walking and walking to the bigger fields, and they don't know what's happening at different parts of the field. So that's what we're trying to achieve here.
More questions?
Please, yeah, I'll be happy to discuss. We're
Any
proud of this.
opportunity to extend to other crops, let's say like sugar beets, things like that?
Very, very appropriate question. We are trying to get this into grain crops as well. and some of the vegetable crops as well. So
Those
highly,
are underground then.
highly possible. We have not tried this, but if there are collaborators, because we don't grow, sugar beets or things, those kind of crops in our region, but with potatoes certainly, maybe.
Right.
But in different parts of the country, certainly this approach can be made translatable. We started this from just single view learning, like just simple machine learning, and we found a lot of inconsistencies in the data because it's multiple states. We are already tackling like 10 plus trials every year, multiple states, so there could be a lot of noise in the data. And so we wanted an effective method that can normalize the data plus make it consistent throughout so that we don't have to remove any kind of even outliers. And that's where we came up with this multi-view stacked ensemble learning that gave us some very much good extended results. So yeah, sooner we'll be publishing these maybe 3 years of data.
Thank you.
Thank you.
So we have about 4 minutes, and I want to use those 4 minutes. There are some evaluations, and if I have to say, I'm pretty sure none of you have done it. So good opportunity if you can do it and pass it and do the evaluation. The organizers will be really thankful. It should be quick. Lucas, you're here? Okay, good. We'll read till then. Okay. We'll start at 11. Because you don't know, people might want to listen, they might come and okay. For people who just came in, there's a sheet for doing the evaluation. Just scan the QR code, please. And our next presenter is our own from Mississippi State, Lucas, and he'll be talking about a new framework for agricultural field boundary extraction based on segment anything model and sentinel imagery.
So good morning, as is information, I'm Lucas, and today I'll present my work of my collaborators. The title is A New Framework for Agricultural Field Boundary Extraction based on the segment anything model and sentinel tree metric. So just to recall, in a crop production system, an agricultural field is basically the fundamental spatial unit. because everything happens in the field. All agronomic operations, I harvest the field, everything happens in the field. So, due to this reason, it's very important to know the field boundaries. And when you think about extracting field boundaries, using satellite images, it's a very good approach. We have a lot of satellites out there, but Sentinel-2 is probably one of the best options because it has global coverage, a good spatial resolution, and it is freely available. And when you think about algorithms or methods to extract field boundaries from images, we have many options, but in this study, we are focusing on segment NP model, which is a very popular model for instance segmentation, and generally provides very good results. So we have a huge potential to apply SAM to extract field boundaries, but we also do have some important open questions. For example, is SAM feasible under different agricultural contexts? How should the model be configured? So we have some open questions. I'm trying to answer those questions. The objective of this study was to develop a new SAM-assisted crop field extraction framework named FieldSeg, used in 2022, Sentinel-2 temporal composites, and present the lessons learned implementing this foundational model in 8 relevant agricultural regions across the world. In this study, we consider 8 study areas across the world, as you can see in this map. Each area is a 10 by 10 kilometers area. And our first and more difficult step here was to manually delineate all field boundaries within the study areas. And then this reference data set supported the validation of our method and our experience. In terms of data sources, we used all Sentinel-2 images available in 2022 with cloud cover equal to or less than 40%. We used the bands red, green, blue, near infrared, and shortwave infrared 1. And also we added some vegetation indices because we observed that they have a good potential to highlight the field edges. So that's why they are there. And I didn't mention so far, but when you are using segment and field model, you can use this model to extract every object within an image. But here we are just trying to extract field boundaries. So we can apply, we can extract everything, but we need to post-process to remove non-crop field objects. So to perform this test, we created an annual cropland masks based on Google Dynamic Board. So based on this product, we know where we have crop and where we don't have. So we can apply this data to filter the objects that were extracted using SAM. As I mentioned, I have a lot of images over time. I have a time series. In here, we use some temporal metrics to compress the time series into a single image. We evaluated different options, including mean absolute deviation, standard deviation, different quantiles, and also principal component analysis. We also have different bands and vegetation indices. So we explored different combinations. Because when you use SAM, we need to fit the model with a 3-band image. So even though we have many, we have to select 3. And then we propose 3 different combinations. The first one is a 2-color composite. The second one is a composite based on the bands near infrared, red and green. And the last one is a combination of 3 different vegetation indices. So as you can see, when you have different combinations of bands and temporal metrics, we have different visual appearance and visual quality of the final image. This flowchart here will show us an overview of the proposed framework. So as I said, we have a time series of Sentinel-2 images, and then we have some of the original bands that we selected, and we added some vegetation indices. From this set of bands and vegetation indices, we select 3, and here we have different options, different combinations. The next step, we will use a temporal metric to compress the time series, and again we have different options. Once you get in this stage, we split a large Sentinel-2 image into smaller patches, which are basically smaller subsets, smaller images. And then we scale each patch to an 8-bit scale. We apply a resampling, and here we investigated the use of resampling the 10 meters resolution to a 5 meters resolution using a simple resampling technique, distributed resampling. In this case, we evaluate both the original resolution and the resampled one. And here we get a final image that we can feed SAM. And in this study, we also evaluated different image encoders and configurations. The output of SAM will be segmentation masks for each patch. Then we also perform some post-processing on these masks. We merge the patches again to reconstruct the final image. We apply the selection of crop field objects, and the final output will be the crop field boundaries. To validate our framework, we assume as a correctly structured field, only a field that intersects only one reference field and overlaps at least 80% of its area. Otherwise, we don't consider a field as correctly structured. We use some metrics to evaluate the results. The main ones are object-based overall accuracy and the ratio of correctly structured fields over the total amount of reference fields. In terms of results, we can see that when you use the Penny combination EI base, which is vegetation indices, and the temporal metric MAD, we got the best performance. As you can see here, this column, the second column, is the best combination. And you can see, if you compare to the others combinations, you can see that the field edges are more highlighted, which is very good to extract field boundaries. After performing extensive experiments, we propose 3 different general configurations. The first one is a general configuration for general purpose. The second one is focused on the small fields. And the last one is focused on medium to large fields. In terms of final performance, our framework achieved a promising performance for areas with medium to large fields, being able to correctly extract between 54% to 81% of the fields. But for areas with small fields, we had a moderate to low performance. I just showed some numbers, but here are the graphical results. These 3 areas here are areas with medium to large fields. We can see the input image in the first column, the reference fields in the second one. The third column is our predictions. And here, when you see a green field, it means a field that was correctly extracted. If it is blue, it means that there was an undersplit. If you see red, it means oversplit. Yellow is an omission, is a field that I didn't capture. And purple is commission, is when I predicted a field, but I shouldn't be predicting that field. So you can see that here, we were able to extract most of the fields correctly. But when you go to the areas with small fields, it's much more challenging. So in the last column, we have our most optimized approach. It's better than the first one that we started our study. But even though it's a challenging scenario here, we also compare the performance of our framework with an existing framework. So here you can see stable our results in terms of object-based overall accuracy for each study area. The first column here is baseline and existing framework. And the 2 last columns are the results for our framework. The general configuration is a general configuration for everybody. And the last one is when I use a configuration for small fields and a configuration for large fields. And basically we can see that the last one is the best configuration, and our frameworks got better results in all scenarios. Finally, we performed a large-scale demonstration of the capabilities of our framework. We run the framework in 4 global areas, covering 1 billion square kilometers, and carried out a visual analysis. Here you can see, for example, for Brazil, we have very high variety of shapes and sizes of fields. We have fields with area ranging from 0.5 to 70 hectares. And overall, we find a good quality, a good segmentation quality here. For Germany, we have fields ranging from 0.5 to 14 hectares. And again, we observe that a good ability to extract the fields. But for India is the most challenging scenario. Here we have fields between 0.5 and 6 hectares, but most of the fields are very small and the shape of the fields is very complicated, heterogeneous. So here we have the worst results here. Overall, we can say that the framework is still not ready to operate in such a challenge area like India. And in the United States, we also have the good results, and the field range in terms of area ranges from 0.5 to 60 hectares. As final remarks, we can see that the proposed SIM-assisted framework demonstrated promising capabilities to segment crop fields with different shapes and sizes without additional training, which is very important. The performance for small fields was moderate to low, and future studies could consider higher resolution image, which is a potential limitation of this study, or also super resolution techniques. When compared to an existing framework, our framework exhibited superior performances in all study areas, and the proposed framework is a potential solution for large-scale field boundary extraction. Thank you. If you have questions.
We have plenty of time for questions. Question?
First of all, again, I like the work. I have two questions. First, does it work on paddy fields?
Does it work?
Paddy fields.
You can use SAM for everything. It's able to extract every kind of object, but as I said, we need to post-process to remove objects that you are not trying to extract. So as long as you have a mask that you can use, you can theoretically extract anything.
I want to apply in my country and also in some ASEAN countries where paddy fields are kind of common, and we can have a field boundary data set, which are very critical when it comes to MRS. So I want to apply. The second question is, what would be the reasons why you kind of fail to extract field boundaries for the small fields? Is it because of the resolution of the satellite image or something else?
The resolution of the satellite image is the main factor, because even if you look at the image, you have difficulty to see the fields. The resolution that we use here is a 10-meter resolution. So if you have a field with half hectare, it's difficult to see the field. And in some situations, small fields tend to be more heterogeneous, so it's more difficult to understand the boundaries. So we have two main problems: resolution and field complexity.
So if we need to, if I want the model to work on a smaller fields, like do I need to consider like better satellite images like Planet? Like I think they provide better resolution.
Yeah.
Do you think like the images or the data from that satellite could improve the model?
Sure. We are currently working on next step of this work. We are using PlanetScope images and super resolution techniques to significantly improve the quality of the image, and you are getting better results now.
I will keep on because the field size of Japan, most of the field is less than 1 hectare. If we could, like achieve it, that's really good. Lots of time. The government will like it because I can use the data for tax purposes.
We appreciate it.
There's still time for one more question. Yes.
Quick question. Actually, congratulations for the presentation. Really exciting. My question is, like, have you tried to apply the same models for fields that you have no crops there?
No crops. The model can extract, but sometimes your cropland mass sometimes may remove. So sometimes we have like two two parts of the processing framework that we need to work. So I saw a lot of times that the code has been moved to Docker.
Let's thank the speaker. Our next presenter is Yin Yang from Mississippi State, and she's going to be talking about developing an integrated application software for remote sensing and machine learning utilization in agriculture.
Hello everyone, thank you for coming here. I'm from Mississippi State, so show my welcome. And then my name is Jin Yang. Today I'm going to present our work. Actually, it's a tool I designed for the research in this group, and then help you to easily use machine learning. So this is kind of collaborative work between MSU and the USDA. We call our model, we call our tool as AgriLearn. Before we dive into the details, I'll start to go over the key topics I'm going to cover in this presentation. So background, tell you why I do this, and then go to the AgriLearn overview, give a briefly overview about what it is. Then we'll go to different models, see the functions of it. Finally, give you a quick preview, and then we'll see what is the future, what we can do. So, I know everyone knows machine learning is everywhere. Everyone uses it. And then in agriculture, of course. So a common method used in agriculture, traditional machine learning, deep learning, and advanced machine learning like ensemble models and explainable machine learning like Shen, and Long. We want to explain the model you train. And then if we want to use this method, also we know this flow. We need data, we need analysis data, we need purpose data, and then train the model to get it done. So, and the remote sensing actually provides a very low cost way to collect data. And then in agriculture, for some parts, for some tasks, we don't directly use this image or whatever go to your model. You want to extract some information from the remote sensing data and feed it into your model, and then get the result. So it's super powerful, but I'm not sure if there's any problem when you use it. So, but I heard from some people that say, okay, I don't know how to code. And then there's so many hyperparameters in some different models, right? Which one is best for my performance? How can I adjust it? And also it's it's a black box for me, how can I explain it, right? And also, you say AI can help you a lot. Yes, I use ChatGPT to help me to build this system, build our GUI. But the thing is not always they can give you a good result. Another thing is that you cannot directly upload the data to the ChatGPT to help your analysis because security is concerned, right? So, and also for remote sensing data, like I said, we want to extract some information from it. That is kind of, the field is kind of complex, time consuming. How can I help them to solve this problem? Based on this concern, we have our AgriLearn. So, what is AgriLearn? You only need to know, I want to make your life easier. Okay, that's the tool. And then I streamlined the whole processing, like remote geo-image part for the remote sensing data extraction, and then we'll do the EDA part to help you analyze your data, to visualize your data. Now, after you analyze it, you are going to pre-processing. I want to clean the data. I want to transform the data, then make it ready for machine learning and model training. After you use it, okay, this model I can use it in the future, right? You want to save some place and they use it in the future. So train the machine learning model that help you to reuse it. In this workflow, actually, we develop all these functions, but it's based on the deep learning part. So the function, anyways, make you easy to use machine learning, not make it smart. It means I'm not focused on, okay, I train a very real model and then you use it. It's not that purpose, make everything easy to use machine learning. You need to process, you need to analyze still that. So we'll go to the GUI part. So for this part, got it. So so based on that concern workflow, actually I built this GUI system in Python framework. And then, there's 5 models here, and each model we didn't hard connect to each other because we want more people to access to it. and then go to access to it. So everyone can use it any model you want. And then you can just direct click the button and go through different model. And the right part will give the details, like give some introductions, how you use it, what's the function of it. Okay. So now we'll go to the GeoImage model. When I developed this model, I was thinking what kind of features you want extracted from the images. So in agriculture, I felt like, oh, they need color ratio, oh, they need the vegetation calculation, oh, they need clip some small image from the large image, right? And then how to, based on these requirements, I said, okay, we have these kind of functions. Okay, I need pixel level segmentation. I need to calculate the vegetation index and the image clip, of course, and then we will have a data set. And then after this one, we will go to the EDA part. So the EDA part purpose is kind of help to visualize your data set, to see how to, present some kind of statistical analysis result. You can see the feature distribution. You can see if you have outliers, you have some risk values, and where it is. And also, it's like for each feature, for the features you want to see the distribution. For any two features, any more features you want to see their relations. So we provide more visualization method that let you choose visualize it. You just select different things you want to visualize to see it. And then also for some people they may don't know what should I process for my data set. So give some basic recommendations. Okay, you have misvalue, you have to process maybe, you have liars, if you think about it, maybe you need to process for some people, okay. And then after EDA, you visualize data, you analyze the data, you will go through the pre-processing. For the pre-processing there's many pre-processing functions, like you need to handle the misvalue, there's so many methods. You need to handle like the outlier detection and something like that, and then it's there's so many, but for each one they do have different methods. And also for different people, for different data sets, you want to make this kind of processing flexible. Maybe this one wants to process the data like misvalue first and then go to another one. But maybe another person they don't want to do that. So we make it much more complex, flexible. So the people you can just adjust the processing order, and then you'll get your processing as you're required. And then after processing, we will go to the machine learning part. That is like, wow, there's so many machine learning models. There's ensemble, there was, and then it's like, what was that? And also, actually, this model, especially for the ensemble and the external and the traditional machine learning model, they do have some overlap. Your external machine learning model actually is to explain what happened when you train the model. And then for the ensemble machine learning is to combine several individual models together to give you the better result. So we combine them together and then let you to easily use it. So you can directly click the button, and then we'll pump up for each method. We will pump up sub windows, and then you can adjust these parameters by yourself. Or maybe you can use some gradient search or random search to use like hyperparameter turning. We will provide it for you. And then run it, the result shown here, and then you can click the explain with sharp or explain with long to explain the result. So it's like also we think about maybe people want to compare their multiple models. If they want to compare multiple models, what can we do for that? Run on. Because right now, as long as you know, it's like in agriculture, collect data is kind of not easy, and especially in the research area, our farm is small, so our data kind of limit is not very large. So you can run all the data, it cannot take very long time. But in the future, maybe we need to include this part. Okay. So then, after training model, you want to save it someplace, and you want to use the future, and then here you can directly save it here, and then you can upload some data set and directly use it. There's like also have some information to explain the model. Like, you know, there's some information about the model, you can extract it and see that. So, quick conclusion is some tool I want to make life easier, but still developing. And so if you have any suggestion or something, advice, and just let me know. And for the future work, actually, what we are doing actually now is like want to embed the deep learning part, and also the image data set analysis, processing, and model part. Another one is like we are developing a web-based application and then make people to easily use it. For the others, it's kind of more future work. Okay, thank you.
We have, yes, please.
Congratulations.
Thank you.
Based on what I understood, you have some data sets that you can run on the tool.
Yeah.
Can you describe what kind of data sets have you tested that you work for classification, such as some satellite data sets or air image, drone images?
Okay, so it's like we say we do have different models, and for different models, especially currently we are working on the tablet data. So it's like you need to upload the CSV or Excel data, and then we'll focus on that. For the geo image part, of course, you can upload RGB image, multi-spectral image, and then at the same time, I want you to upload your shape file, so they can click the image based on each plot and extract the information based on each plot. Yeah.
Dr. Muller?
Hello.
Yeah.
Thank you for your presentation. Do you have any limitations on the memory or the size
Yes.
of the data sets?
Yeah, that's a really good question. Actually, so right now I just want to make every function works real, and then next stage we want to improve the storage limitation and make the run more smoothly and faster.
So right now, what's your, what size of a scene or whatever can you handle in terms of like, gigabytes or terabytes of data for one run of this model?
I didn't test on that part yet.
Okay.
Yeah, I will try. Thank you for your presentation.
Dr. C?
This is really cool.
Thank you.
Have you tried like keeping a notebook for even
Yes.
more extended application?
Yeah. Yeah, we'll do that. Yeah.
Really cool.
Thank you.
Does this manage categorical values in the data set as well?
So,
Like in not only continuous variables, but like categorical parts it manages?
categorical.
Like,
So the question is, does it only take numeric continuous values, or can there be categorical data sets like?
and it is a software or an application that I need to download in my computer?
Yeah, well, yes, that's like after we finish all the parts and make everything work well, you can download it and just run like the APP. That is our purpose, yeah.
I see it's really user-friendly.
Yeah, thank
And
you.
this is a standalone. So we have another graduate student develop an internet-based, maybe even the tablet and the cell phone version.
Dr. Singh?
Well, provided I understood it correct,
Yeah.
is the data from one model available in another model?
It's like if you, it depends on you actually. If you want, actually you will have the interface. You can upload the different data, and then it's like you can just drag into different models if you want. And another thing is like of the different models, you will create a different data set, right? For the persistent data, they will have an extra data set, and then you can directly actually provide some interface. You can directly go to the machine learning model, or you can go back to that one. They can directly use that. Yeah. Thank you.
Just one quick question.
Yeah.
When do you think it will be available as an app or a tool? Do you have like a timeline?
I hope it will be soon. At least, there's a lot of detail right now. It's like,
Actually, I talked to her,
Yeah.
this kind of thing, you never end. Always the room to improve. So at some point, I think right now, if you really request, we can deliver. So,
Yeah.
so we're not put online yet. We are going to, and
somebody suggests us to write a manual even for it, so how to implement. I think that's a good suggestion. So, yeah, looks
You
like-
can do different versions.
Yeah, different version, yeah, right. So, yeah.
Any more questions? Yes.
For your remote sensing data, do you use some transformation of your data to make it more efficient storage or transferring?
We don't do it right now. Yes, like we just like you already do the mosaic of the data, image data you upload it, and also the shape file. We want you. What I did right now is like one thing is like help you to extract the kind of cover ratio, like into the segmentation, and then another one is like a plot-based like vegetation index. Yeah.
And that, just a suggestion, maybe
Yeah.
if you want to overcome some of the barriers in memory mentioned before.
Yes, yes.
And maybe some of the studies we did,
Yeah.
learn from those NASA folks, they know how to do it really well.
Thank you, thank you.